Welcome back to Things You Don't Know. Today, we're talking about rocks. Yeah, what they are, how they form, and three major rock types, and why rocks have mattered to human life from prehistory to modern industry.
And we'll also focus tonight on the mechanics and processes, how rocks form physically and chemically, and how they change over time, and how people use rocks as materials, tools, and infrastructure.
As your resident historian, I'll add historical context, how societies understood, classified, and relied on rocks across time.
What is a rock and what isn't it? Well, in everyday language, a rock means almost any hard natural stone. In geology, the term is more specific. A rock is a naturally occurring solid made of one or more minerals, or in some cases, mineraloids like volcanic glass.
So the key point here is that rocks are aggregates. They're built from smaller components, minerals with specific chemical compositions and crystal structures. Quartz, feldspar, and calcite are common examples.
Rocks are not static objects. They form, break down, and transform over time through geological processes operating on timescales far longer than human lifespans.
Now let's talk about the rock cycle. The organizing framework for understanding rocks is the rock cycle. It describes how igneous, sedimentary, and metamorphic rocks are connected through processes like melting, cooling, erosion, burial, heat, and pressure.
Importantly, the rock cycle is not a single loop. A rock can enter the cycle at many points and follow many possible paths. For example, an igneous rock can become sedimentary without ever becoming metamorphic.
And from a mechanical standpoint, the cycle is driven by two energy sources: internal heat from the Earth's interior and external energy from the sun, which powers weathering and erosion.
Yeah, let's take a little closer look at igneous rocks. Those are rocks that from melting. Igneous rocks form when molten material like magma or lava cools and solidifies. This is the starting point for many rocks in the crust of the earth.
Absolutely, Dr. Weaver. And when it comes to igneous rock, there are two main categories: intrusive and extrusive igneous rock. Intrusive igneous rocks form when magma cools slowly beneath Earth's surface. Extrusive igneous rocks form when lava cools rapidly at or above Earth's surface.
Now, granite is a common intrusive igneous rock. Its large crystals indicate slow cooling. Basalt is a common extrusive rock with very small crystals due to rapid cooling.
Mechanically, cooling rate controls crystal size. Slow cooling allows atoms time to arrange into large, visible crystals. Fast cooling freezes atoms in place before large crystals can form.
Igneous rocks are important because they form much of Earth's crust and provide the raw materials that other rock types are eventually made from.
Now let's talk about sedimentary rocks, rock from pieces. Sedimentary rocks form from material derived from pre-existing rocks. Weathering breaks rocks into fragments or dissolves minerals. Erosion transports them, and deposition settles them into layers.
Over time, burial causes compaction and cementation, turning loose sediment into solid rock. Now, rocks end up buried or submerged underground, mainly through a few everyday earth processes. Sediment burial, that's perhaps the most common, is from wind, rivers, glaciers, and oceans, carrying sand, mud, and gravel that get deposited in layers. Over time, newer layers pile on top, covering older rocks and pushing them deeper. Another process is lava and ash cover. Volcanic eruptions can blanket the land with lava flows or ash. Once it cools and hardens, it forms new rock that buries whatever was underneath. Another factor is tectonic movement and subsidence. Parts of Earth's crust sink, like in sedimentary basins, or get pushed down as plates move. So rocks end up deeper, even without a lot of new material on top. Another factor, sea level change or submerged in water, then buried. If sea level rises or land sinks, an area can become underwater. Then marine sediments settle on top and bury the rocks. Another factor, landslides and debris flows. Large slope failures can rapidly dump tons of material downhill, covering rock surfaces rather quickly. Once buried, pressure and heat can change rocks over time by compaction, cementation, metamorphism. But the basic, how they get underground, is usually stuff piling on top, land sinking, or both.
There are three main sedimentary categories. Classic sedimentary rocks like sandstone and shale are made from rock fragments. Chemical sedimentary rocks form when minerals precipitate from solution. Organic sedimentary rocks form from biological material.
Limestone is a key example here. It forms from shells and skeletal fragments of marine organisms, making it both a geological and a biological record.
Sedimentary rocks are especially important to humans because they often host groundwater, fossil fuels, and fossils. They also are good for recording Earth's surface conditions through time.
Yeah, it's fascinating, isn't it, Chandler?
I think it's very fascinating.
Yeah.
What about metamorphic rocks there, Dr. Weaver?
Well, yeah, that is an important thing. Metamorphic rocks form when existing rocks are altered. And that can happen by heat, pressure, or chemically active fluids without melting.
The word metamorphic literally means change form. Like, it almost reminds me of the term morph, change into. The original rock, called the protolith, is transformed into a new rock with different textures and mineral structures.
Marble is metamorphosed limestone. Slate is metamorphosed shale. Gneiss often forms from granite or sedimentary rocks under high pressure and temperature.
Mechanically, metamorphism reorganizes minerals. Atoms move within solid rock, forming new crystals aligned with stress or temperature gradients. Yes, atoms in a solid do move, just not the way they do in liquids or gases. In a typical solid, atoms are locked into fixed positions in a lattice or structure, but they vibrate constantly around those positions. more vibration when a solid is warmer. Over longer times, some atoms can slowly shift places through diffusion, usually very slowly in solids, but faster at higher temperatures or long defects like grain boundary. In some solids, like glass, the structure is disordered, but atoms mostly vibrate. Large scale rearrangement is just slow unless heated. So, constant vibration always and slow migration sometimes, especially with heat and imperfections.
Metamorphic rocks tell us about conditions deep within the crust and at tectonic plate boundaries. It's very interesting. It's a fascinating record.
One of the most important things that rocks give us is a sense of time. Many rocks are millions or billions of years old. Think about that. That's amazing, I think. Don't you, Dr. Weaver?
Oh, absolutely. Radiometric dating uses radioactive decay in minerals to determine absolute ages. This is how scientists know Earth is about 4.5 billion years old.
Sedimentary layers provide relative time. Lower layers are generally older than layers above them, allowing reconstruction of Earth's history even without exact dates.
Rocks are truly Earth's archive. They preserve evidence of ancient climates, oceans, volcanic eruptions, and mass extinctions. Rocks did play a role in early human history because they played a central role in early human survival. Stone tools appear in the archaeological record over 2 million years ago.
That is quite a long time, wouldn't you say?
Just a day or two.
Yeah, it's been a minute back. So from a material standpoint, certain rocks like flint and obsidian break with sharp edges, making them ideal for cutting tools and weapons.
The Stone Age is named for this reliance on rock technology long before metalworking.
Rocks also provide a shelter, grinding surfaces for food processing, and pigments for early art.
As societies developed, rocks became building materials. Stone structures offered durability and permanence.
Granite, limestone, sandstone, and marble were widely used because of their strength and workability.
When you look at many ancient monuments from pyramids to temples, they're essentially large-scale rock engineering projects.
Rocks also supported agriculture. Weathered rock forms soil, supplying minerals essential for plant growth. Now let's talk about rocks in modern life. Modern society still depends very heavily on rocks, still to this day, even if we don't always notice it.
Yeah, metals are extracted from mineral ores found in rocks, iron, copper, aluminum, and rare earth elements. They all come from geological materials.
Concrete is made from limestone-derived cement and aggregates like gravel and sand. Roads, buildings, bridges, all kinds of infrastructure depend on rock products.
Silicon, which is derived from quartz, is quite foundational to electronics and computing.
Yes, indeed, it is. Even energy systems rely on rocks. Trump's favorite, coal, which is the filthiest and most expensive, uh, oil bearing sedimentary formations, and geothermal reservoirs. Now let's go to environmental and societal roles. Rocks influence hazards as well. Earthquakes, landslides, and volcanic eruptions are all tied to geological processes.
Understanding rock behavior helps engineers design safer buildings and infrastructure.
Rocks also affect water resources. Aquifers form in porous rock layers, supplying drinking water to millions. The aquifers act like a bowl and contain the water.
From a systems perspective, rocks underpin ecosystems, economies, and risk management.
Yeah, rocks may seem inert, but they are active participants in Earth's systems.
They cycle materials, store energy, and most importantly, they preserve history.
Studying rocks helps us understand where resources come from, how landscapes form, and how the earth changes.
And because human society is built on rock-derived materials, geology remains directly relevant to today's life.
From molten magma to layered sediments and transformed metamorphic rocks, the three rock types tell a connected story about Earth's processes.
Rocks have shaped human tools, cities, technologies, and environments historically and today.
You're certainly correct, Chandler. Well, we could keep on discussing this forever, but I think that concludes our episode on rocks. Please leave a like and a comment, folks, and come back soon.
Bye for now.
Rock on.